Hello everyone, my name is An, full name is Nhat-An. Today I will introduce about the meta barrier as low frequency block and its application in ground vibration reduction. The authors are me, Nhat-An, and Professor Lee Chin-ho. We're coming from the Department of Ocean Engineering, Pukyong National University. Next is the content. These are the contents that we will go through from this presentation. Introduction, we will talk a little bit about the study background, the objective of this paper. Next is the periodic structure and frequency band gap. The frequency band gap and dispersion relation will be first interpreted, and next the unique cell configuration of the proposed meta barrier is evaluated, and come after that are the lattice constant, hollow core dimension, and width of the rubber. Third one is the application of the meta barrier, which consists of a 3D numerical model in the time domain, and the comparison between natural ground and the ground reinforced with the meta barrier. Lastly, some conclusions and discussions are derived. First, introduction. For the study background, as you can see in the figure 1, it is the Rayleigh wave motion and its damage to the structure. Rayleigh wave is an elastic wave that travels a considerable distance over the Earth's surface and causes many damages. Considering the valuable properties such as power stations, ancient buildings, biology labs that consist of bacteria, viruses, some kind of dangerous viruses that can affect the environment, museum with precious control relics, and so on. It is of importance to design a shield around the protect building, the protect structures to prevent seismic waves and also severe damages. Efforts have been made to create structures to reduce the vibration, such as soil cylinder cones, cross-shaped holes, resonant metal wedges, and so on. The objective of this paper, even though great progress have been conducted through decades to control seismic waves by different types of structures, it is still insufficient to cover broad ultra-low frequencies. In the present paper, a meta barrier is proposed and numerically examined. It aims to shield structures from seismic Rayleigh waves in the frequency range of 2 to 20 Hz, which is common in earthquake spectra. Second, periodic structure and frequency band gap. The frequency band gap and dispersion relation will be introduced in this section. The governing equation for motion of waves travel in homogeneous media is like equation 1. According to Bloch theorem, the displacement equation will be like in equation 2, and according to the periodicity of the periodic structure, we have the conditions like equation 3. After substituting the equation 3 to equation 2, we have the periodic boundary conditions. And applying the periodic boundary condition, we have just derived above from equation 4, equation 1, and equation 5. So we can obtain the eigen value from this equation. We can find out the dispersion relations, and from that we can determine the frequency band gap. In the figure 2, the periodic boundary conditions are applied in the irreducible size of the unique cell, and also the variance of K wave number in the first irreducible Brillouin zone is depicted in figure B. Next is some examples of the frequency bandgap and dispersion relations. In the figure 3, you can see there are some different unit cell constant, like just a 0.5 meters unit cell and 5 meter unit cell. There have some different value of frequency bandgap and dispersion curve. The frequency bandgap is the frequency range. As you can see in the figure, they are the gray area that can prevent the wave from propagating through the material within the range. For example, if the frequency bandgap is from 18.03 to 30.54 Hz, the wave traveled with the frequency range around 20 Hz cannot transmit through the unit cell. The dispersion curves are the relation between the frequency and the wave number. The red lines that show the most that wave can travel through the material. Next is the unit cell configuration. In this paper, we propose this kind of unit cell, and it is a scoop which has 3 components: concrete at the coat outside, the rubber that link between the concrete and the cast iron, and also we have a hollow air core at the center. Table 1 shows material properties. In the figure 4A and B, some configuration dimension we have showed, and also the 3D view of the unit cell. Next, the lattice constant evaluation is checked. As you can see in the figure, we just changed the lattice constant A from 0.5 to 6 with an increment of 0.5 meters. Different behavior we can see in the table 2 and figure 5. As the lattice constant increase, the bandwidth decrease, and the frequency bandgap in the lower frequency range can be observed. Depending on the purpose of vibration reduction, a suitable lattice constant should be properly chosen. Next is the hollow core dimension evaluation. Now we just change the parameters A3, and we can see some difference in the behavior. The table 3 and figure 6 shows the difference of the frequency with different hollow core dimension. So with the bigger the hollow core, the higher FBG can be achieved. However, the bandwidth will decrease at a specific rate. The frequency bandgap does not change much in the amplitude when we reduce A3, so does the bandwidth. For example, at the value of the ratio A3 over A equal 0.3, from that to 0.05, we can see the amplitude have not changed much. Next is the width of the rubber evaluation. Now we just change the parameters W with different ratio W over A, and the results are shown in table 4 and figure 7. The wider the width of the rubber coat, the higher frequency can be achieved, and the bandwidth is also broadened. The unit cell with different rubber width, which cover a wide bandgap, can be used for multiple purposes. Next is the application of the metabarrier. Now we construct a new 3D numerical model using the console multiphysics software package. As you can see in the figure 8 is the configurations and also the location of the components we have made. The first one is the dimension of the whole model with 100 meters length, 50 meters height and 5 meters width, and we use an excitation with this kind of function, a harmonic excitation force on the line, which is set 27.5 meters from the front of the metal barrier, and after 37.5 meters from the back of the metal barrier, we check on an evaluation point on the ground surface. Low refracting boundary conditions are set at both ends and also the bottoms of the model to have better results, and also we will not have the refraction back from the waves if they move towards the edge. PRX boundary condition is also set at both irreducible vertical sections. Next is some results of the numerical model. The termination time is set to seconds, and in the first one we want to check the soil with the lowest shear wave velocity, 15 meters per second. And you can see in the figure 9 are the comparison between the responses such as displacement, velocity, and acceleration. In this comparison, we just compared the natural ground case, 1 layer of metal barriers case, and 3 layers of metal barriers case. In the previous slide, we can see it is the 3 layers of metal barrier, and now we can see there are some comparison between the responses, and you can see that the vibration has been reduced a lot effectively in this kind of soft soil condition, especially in the vertical acceleration, and the amplitude reduction of vibration is showed in table 5. 87% is can be observed in the table 5 for the velocity response. Next, we consider the soil 2 with the stiffer condition. The soil 2 will have the shear wave velocity of 50 meters per second, and also we'll check the displacement, velocity, and acceleration. The reduction is reduced, but it's not reduced like that in the soil 1 condition. Now we check the 1 layer, 3 layers, and 5 layers case compared to the natural ground. As you can see that if we increase the layers, we can have better reduction, but from the 3 layer to 5 layers, we cannot have much change. Next is the last soil condition, soil 3, which has the shear velocity of 200 meters per second. We also check the displacement, velocity, and acceleration. Now we check the 3 layers and 9 layers case, and as you can see in the figure that the 9 layers show a very high effectiveness when reduce the ground vibration compared to the 1 layer and 3 layers. But it also costs a lot of money, a lot of construction cost. Some conclusion and discussion are made in this presentation. The proposed unique cell of metal barrier can achieve low frequency bandgap. with different configuration and variants of component dimension. Multiple purposes in vibration reduction can be applied. In different soil conditions, the metal barrier with 5 meter unique cells show high effectiveness on reducing ground vibration. Number of layers of the metal barrier should be chosen carefully to reduce the cost of the construction while remaining good performance. For example, the three-layer system of metal barrier is smaller than that of the other case, but still have great reduction compared to 5 layers in soil 2 and 9 layers in soil 3. That's all my presentation, and thank you for your attention.